Thanks, Christian, for the introduction. So I'm Dhiman, and I'm happy to announce our result on Cipher here. This is a joint work with Christina, Obhik, Kaito, Gautam, Hadi, and Valentin. Okay, so I like to call this part of the presentation as the life of Pi. So we want to introduce you this Cipher first, and let's see what we know about it. Okay, so all of us know about authenticity encryption. We had a lot of talks during the previous days, and I will not go into the details, but it is, Cipher is a submission to the Cipher competition, and it is presently in the second round. In the first round, there were 6 variants, which were later in the second round, they reduced it to 4. And very recently, they have also proposed to lightweight variants, which are not a part of the Cipher submission, and there are 2 versions in that. And the mode of operation is inspired by Sponge, but it's really difficult to make out from directly by looking at it, but it's inspired by Sponge. And it's really supports this parallel computation. So it's one of the main motivations of the design to support these parallel computations. Internally, it instantiates this Pi function, which is obviously, you can understand the name of the cipher comes from that. And these are actually this table shows all the variants that are presently available. And these are all in version 1 and 2, and these are the ones dropped, and these are the light one versions. An important thing is it operates on this word size, omega, so you'll see a lot of omega in the presentation, so you just get familiar with this. And as terms of the nonce, it uses a combination of this PMN, public message number, and the secret message number to instantiate the nonce. One important thing is that it allows the nonce size to be, SMN size to be 0, so just remember that. Now, the basic building block of the Cipher is what the authors try to call as a triplex component. And what it is in an abstract sense, it has 3 input, 2 output, among which one is optional. And as you can see, this is the inside of the triplex component, which instantiates Pi 2 times inside the Pi function. And in case of the associated data, it just gives the partial tag as an output, while in case of the plain text is also the ciphertext also. That's why it's called the optional out here. Okay, so this is the basic building block. Now let's see how the Cipher evolves. So it starts by concatenating the key with the public message number and a standard 10 star padding, and called Pi once. Then the counter is taken from the 64 bytes from this capacity part. Okay, so this is the capacity part, and this is the rate part as regards to Sponge. So it constructs this internal state called the CIS, which stands for Common Internal State, and it adjusts the counter accordingly for the parallel branches. The next step is that you can find the triplex component here every time. So it absorbs this associated data and generates this partial tags and does this addition out here, which is actually internally it adds word-wise. It's a word-wise addition. It's a component-wise addition. And finally, it generates it calls this block, which is actually handles the SMN. So the SMN is taken as an input, and this CS is communicated. Finally, we have the message processing phase, where this from this phase, we have the CS double prime, the common internal state for the message processing part. And this part is actually very similar to this, and we have, again, the triplex component for the message processing, so it absorbs the messages and gives the ciphertext output, and the tag is computed in the similar way, taking the tag from the associated data phase, finally giving this tag and the ciphertext as an output. So this is the high-level structure. And as regards the case where there is no SMN, what it does is that it just drops this part, these 2 calls. And to keep things simple, and keeping the naming convention same, we just continue using CIS double prime again. So this relation holds. So this is what it does in case of where there is no SMN, as regards this work. So now let's look inside the Pi function. One thing you should get very familiar is, otherwise you'll get confused, is that this word, actually, this is the basic unit. So it is these are omega bit words. 4 such words make a chunk, and 4 such chunks make the input to this, make the internal state of this Pi function. So this is 1 round of Pi function, and these are the round constants, and it is iterated. And it's an ARX-based design, which is actually based on a function, hash function, which was proposed by a couple of designers of the same team. And in the first round, this had 4 rounds in the first version of the Cipher, which were reduced to 3. So in the second version, they were reduced to 3. And in the lightweight version, they were reduced to 2. So these were the very decisions taken by the designers. And as you can understand, the internal state is 16 omega bits. And you can find the star operation here. And inside the star operation is actually all the ARX things going on. And the start operation, as you can see, is a 2 input, 1 output. So these outputs are equal. Okay, so this is 2 input, 1 output function, and it's invertible with respect to each input. This work, I must say, does not depend on the internal structure of the star operation. So hence, we'll skip the description here. If you want to look at, you can look at the submission document. And finally, these are the present cryptanalysis available for Cipher. The first one was reported by Ford and Laura, in which exploited the weakness in the padding function. And actually, in version 2 of the Cipher, this function was fixed, and they are now using the typical 1-0 star padding. The second thing that the designers claim is something called tag second pre-image resistance, which is sort of an insider attack. That means if you know the key, even in that circumstance, you will not be able to generate a second message from a given message and tag pair. But it was shown, again by Lorno, that in using Wagner's generalized birthday attack, that you could actually violate this claim. Finally, the third claim, thing was by the designers themselves. So this is a distinguisher for one round. And it uses principles which are similar to us, but in our case, actually, we are able to reach 2.5 rounds and, of course, achieve a full key recovery. So, fine. Now we'll make certain observations on Cipher that will help us develop this attack. So there are mainly 3 observations. The first one you already know is that the star operation. So if we fix one of the inputs, then it behaves as a permutation. So this actually helps us in guessing, backward guessing. So if one input is known and we guess one, then we can uniquely derive the one on in the backward direction. So this helps us in the guess and determine phase of the attack. Finally, this is the most important observation that we make. If the pi function is reduced to 2.5 rounds, what we find is that in the inverse direction, I1 doesn't not depend on O4. So if we have O1 and O2 is known, O1 and O3 are known, and we guess O2, then we can go in the backward direction and determine I1, independent of the value of O4. So there is a limited diffusion when reduced to 2.5 rounds. So this is the main basis of our work. So I'll just show you a typical demonstration of what is going on here. So as you can see, these are XXX component again. We know C1, M1 from this XOR. We know the values of O1 and O3. We just guess O2. And O4 is unknown, so we don't care. So when we do this, we go back, and finally we get I1. So determining, guessing O2 gives us I1. Fine, so this is the guess and determine part. And the third observation is on the common internal state. Right, this observation is quite simple. As you can see, to achieve this parallelism, what they do is that they have the common internal state, and they just adjust this counter to achieve the inputs of each of these pi functions. However, the important thing is that 3/4 of this input is same. So this counter is 64 bits. It is added to only one of the chunks, while the other chunks remain the same. So this is something that we are going to exploit later. So let's keep this observation in mind. Finally, we want to introduce this guess and determine attack. Internally, we used to call it the pirate attack, and let's see how it proceeds. So the first thing is the requirement. So we only require one known plain text with at least 16 omega blocks. So if we get that, we can mount this attack. So we start with the first part. The first part, as I think you can all guess, is the guess and determine part, where we want to find out the value of the first input chunk based on the guess of O2. So this is the guessing. We will guess O2. We know O1, O3. We'll recover I1. So this is what we'll get. Of course, see, you remember, each of these is a chunk, so they have 4 omega bits. So we have a possibility of 2 to the power 4 omega guesses for O2. And hence, we will have, for each of these guesses, we will compute this function. We could have put anything else instead of a 0, because it doesn't depend on the value of O4. And we invert this pi function, and we keep the values of I1 in a list. And we do this for all the 16 omega blocks. So remember, we require 16 omega blocks known plain text. So we do it for all of them. Now, what can you say about the size of this list, each of this list? The first thing that we can say is that it's definitely less than 2 to the power 4 omega. Why? Because the function that maps O2i to I1 is no longer a permutation. So there will be collisions. And hence, the list size is going to be less, the number of unique elements in the list. So, and the second thing is actually a result from the size of the number of image points in case of random mappings, and which gives us this bound on the expected size of this list is 1 minus e to the minus 1 times 2 to the power 4 omega. Of course, it's assuming the fact that this behaves as a random function, this mapping. So we have the bound on the size of the list. Now we move on to the second part. So now we have computed all these lists. The next thing that we want to do is intersect these lists. However, we can't do that directly, as you can understand, because each list corresponds to a different input chunk, which are different because the counter was added. So we cannot directly compute the intersection. So what we do is that we try to find, among these 16 blocks, we try to find the block in which case this relation is satisfied. So it gets this j, so the j belongs to this set, and for j, this relation is satisfied. Those counter plus a plus j is 0 mod 8 omega. So what this means is that the least log to 8 omega significant bits of that branch is 0. What it helps us to do is that it helps us to do this trick. We can convert the addition, because the last bits are 0, we can add a value k, and it's actually equivalent to an XOR, provided k belongs to this range. And what it helps us to achieve is that we can now transform this list. To every list, we add this value k, and all these lists now correspond to this value. So all the lists, when they are added this value, when we are adding this k with the list, so we are getting this value for. So since now all the lists are transformed, now we can intersect. And when we perform this intersection, we can recover the value. But of course, the guess could be wrong. So what will we do? So now what we do is that we compute intersection for all the guesses of j. And now we try to know what is the size of this intersection. Basically, we try to claim that if the guess of j is wrong, then the size of the intersection, the probability that the size of the intersection is, the size of the intersection is 0 is very high. So it's very close to 1. So if this is the case, then this helps as a distinguisher. So we'll intersect the lists, and if the size of the intersection is 0, that is, there is no element in the intersection, we know that our guess was wrong. However, if the size is at least 1, it will be at least 1 because we will have at least one element in the intersection, then we know the guess is right. So by doing this only 8 omega times for each of the guesses, we know for exactly one value of j, this is going to be correct, and we can recover the value of j. Now, we proceed to the third part. So now we have recovered one input chunk. Our next aim is to recover the complete input of the pi function. So this is the part. So what we do now is that once we have recovered an input chunk, since we know that the value of the counter, the least significant bits are 0 because of our restriction on j, so we can just recompute any value of ijk plus k by just XORing the value of k with it. So what this helps us to do is that it will help us to finally reduce the number of guesses for O2 that we did in the first phase. Remember, we made 2 to the power 4 omega guesses for O2 to compute the lists. So what we do is that we repeat the process, and we guess O2 and recompute this, and now we have this value to compare with. So we compare this value with the recomputed value, and based on that, we discard the values of O2 which doesn't satisfy this equality. So we will get at least one, of course, there may be some false positives, but we will get at least one value of O2. So based on this, we proceed to the second guess and determine phase. So it's very similar to the first phase, but in this particular case, we already know this part because we have recovered I1. Using I1, we again recovered O2, so maybe we have a few values of O2 here. So this part is known. Now we guess the fourth chunk, that is O4. Once we guess this, it's very similar. We go on deriving, and finally we have candidates for the entire input chunk. So we make 2 to the power 4 omega guesses as before for O4, and we get candidates for the entire input chunk here. Now, what we want to do is that we want to recover the value of the entire input. What we'll do is that we'll repeat this process for 2 inputs and exploit the property that we showed, that 3/4 of the inputs are actually equal. So if we repeat this process, we build 2 lists which have these values, list of these values based on this guess. So these 2 lists we can intersect based on this particular property. And based on this, we'll actually recover the full value of the input of pi. So once this is done, actually the rest of the process easily follows. So we'll now look at both these steps together. So this is the scenario presently. We have this value of pi. We have recovered the input ij. We have recovered j. A is known because it corresponds to the total number of associated data blocks. Only thing we don't know is the counter, the value of the counter. Then this is the only obstacle before us to determine CIS, because everything else is known. What do we do? Okay, we guess. We guess the counter value. Once the counter value is guessed, we can reconstruct all the inputs, because now there's nothing unknown anymore. So we reconstruct all the inputs. We simulate the tag computation in the forward direction. We have these intermediate tags. We now just go in the backward direction, recomputing the tags, and we get the value of T double prime. And we again invert it back. Remember, this is the no SMN case. So invert it back, and we have the common internal state. And now we exploit this, that you remember, the counter is basically lower 64 bits of the capacity part of the common internal state. So we not just verify whether our guess was right. If it was right, we just proceed. If it's wrong, we just repeat for another guess of the counter. Now, once the counter is verified, then retrieving the key is very simple, because the key is just a part of, when you invert the CIS once using pi inverse, is just a part of that input. So now, this was the attack on 2.5 rounds. Now let's look at the full rounds for lightweight version. Obviously, I think all of you can get this idea that this will definitely work for 2 rounds. And these 2 rounds versions were presented in NIST lightweight workshop last year. And yes, the only difference is that they're reduced to 2. The strategy is same. The only difference in our part is the guess and determine phase. So this is the guess and determine phase put together. The phase 1, where we know O1, O3, we guess O2, we recover I1. And once this is done, we know this part, we guess O4, and we recover the inputs. So all other inputs are same. So all other steps of the attack are same. And finally, let's look at the complexity analysis. So the most expensive part of this attack are these 2 phases, the guess and determine phase and the intersection of the lists, computation of that. So obviously, we do it for 16 omega lists, and every time we have to compute this pi function in the inverse direction for 2 to the power 4 omega guesses of O2. So this comes to this many evaluations of the pi function. While in case of the list intersections, our idea is to store the lists as array of bits, where the position of the bit is going to determine whether it was there in the, it gave the value after the inversion or not. And using this, we can compute intersection between 2 lists using just 2 to the power 4 omega bit operations. Proceeding, we have to do maximum of 64 omega square list intersections, so this comes down to this. And what we can see is that definitely, if you compare these 2 values, the amount of pi evaluations that we have to do, this will definitely be more, the cost of that is definitely going to be more than 4 omega. So this is the dominating factor, and so the order of the, so in terms of order, we know that the complexity is going to be dominated by this factor. So it's 16 omega times 2 to the power 4 omega pi evaluations. So plugging in these values, we get these actual bounds. And as regards the memory complexity, we only have to store these lists. So for the first list, we have this, again, 16 omega lists, and since we are going to store them as bit fields, it will take this many bits, 16 omega times 2 to the power 4 omega. As regards the full inputs, you can understand you have to consider the full inputs. Now each input is of size 16 omega, and we have to guess these many values for O4, so it will also come down to this. So the memory complexity is also of this order, 16 omega times 2 to the power 4 omega, and when you plug in this, so it comes down to these many bytes. Now we can look at all the results that we get plugging in all these values. So these are the variants for which we can violate the security claim. So for this security claim, for example, the version 1 and version 2, the Cipher 96, which is the current candidate in the Cipher competition, we are able to attack 2.5 out of 3 rounds. And the security claim was 96 bits, and we have been able to recover with 2 to the power 72 time and 2 to the power 69 memory. Similarly, for other candidates also, one important thing to note is that the data complexity, as I already mentioned, is one plain text with 16 omega blocks. So plugging in the value of omega, we get these blocks. So one note about the SMN. Now this attack works only if the SMN size is 0. However, if you assume that the SMN is known, it still can be adapted if the SMN exists and is known. And however, if you again assume that the SMN is unknown, we can still mount a forgery. If you see, in case of the SMN processing, you have this CS value that is known. So what we'll do is that we'll guess the counter, invert the CIS double prime, and actually make a 1 pi inverse, and this CIS is actually basically this one, so we can verify the value of the CIS and recover the counter. Once the counter is recovered, we simulate the tag computation in the forward direction with one additional message block of any choice, and we can predict we can force the tag. So we have a force tag. So the summary that we can have of our work is that we looked into the security level of Cipher, and we found that the decision of the designers to decrease the amount of rounds from 4 to 3 was a bit too ambitious. And we have been able to attack 2.5 rounds. Important thing, we don't use any property of the star operation. So this is independent of the star operation, so someone might look inside the star operation and extend this half round. Finally, for the 2 rounds, it was like very, very ambitious. We have full round attacks on the 2 rounds, so I don't think people are going to use the lightweight version. And despite the fact it's lightweight, and we could also investigate in ways of protecting against this type of guess and determine attack, which actually exploits the limited diffusion. Okay, so this is the team, and we love to call the team as the pirate team, and so we did this attack in Ask last year, so we have this name for the pirates of the Askabian. So everyone is here, and thank you for listening. So any questions you can ask.